So basically, dark matter is an invisible substance that makes up a huge portion of the universe's mass. The interesting thing about dark matter is that we can't see it directly because it doesn't emit or absorb light. Regular matter, on the other hand, when light shines on it, it reflects off of it and comes back into your eyes. And because of this, we can see it. But dark matter, light just goes straight through it and we can't see it and it becomes invisible. And because of this, it becomes really hard to detect, so we have to infer its presence from its gravitational effects on visible matter, like stars and planets and galaxies and such. And the cool thing about dark matter is that it makes up even more of the universe than regular matter does. So a good example is basically that when you have a table and you put a magnet underneath, and you put a cloth on top of the table, and you put a magnet on top of the cloth, and you put your hand on the magnet underneath the table and you start moving it around, the cloth will move too. And this is a perfect example of dark matter because assuming that the magnet is dark matter, you can see its effects on other types of matter because the cloth will move too, but we don't really know what's happening and how this is happening because we can't see the magnet because it's underneath the table. And this is a really good example of how dark matter really works. The story of dark matter is basically, in around the 19th century, there was a Swiss astronomer named Fritz Zwicky, and he noticed something really interesting about how galaxies move within galaxy clusters. And this movement couldn't only be caused by how visible matter was. And a couple decades later, there was an American astronomer named Vera Rubin, and she further solidified this concept of another type of matter, aka dark matter, by her groundbreaking observations on how galaxy rotation occurs. And she found that the stars on the edges of galaxies were moving just as fast as those close to the center. And this shouldn't happen because the stars close to the center of a galaxy will have a much stronger gravitational pull. And they'll rotate much more faster around whatever the center is, like a star or such. But objects going at the very edge of the galaxy, they won't be as close, so their gravitational pull will be weaker, and therefore they'll rotate much slower around the center. But according to her studies, they were rotating at the same speed. And there had to be some other kind of mass or other substance that was causing this to happen. So moving on from the backstory of dark matter, let's talk about some of the observational techniques used to study dark matter. And one of the main techniques is known as gravitational lensing. And this phenomenon is basically when the gravitational pull of dark matter bends and distorts the path of light from distant objects like galaxies and such. And another really important piece of evidence is galaxy clusters. And when astronomers observe how galaxies move within these clusters and analyze their speeds and velocities and such, these astronomers can deduce how vast amounts of unseen matter, aka dark matter, bind and keep these galaxies together like glue. And dark matter has a really important role in the formation and structure of the universe. So basically, without dark matter, galaxies wouldn't have enough gravitational pull to stay intact, and the universe would lack the web-like structure that we observe today, and the whole universe would just scatter. And that's why dark matter kind of acts like glue and glues the universe together. And just basically imagine dark matter as an invisible scaffolding that supports the visible universe. And its gravitational influence keeps galaxies from flying apart and enables them to form clusters and superclusters and create the unique universe as we observe it today. So since scientists don't know what dark matter really is, there are many possible candidates for it. And one of these candidates are known as weakly interacting massive particles, aka WIMPs. And WIMPs are hypothetical particles that interact really weakly with ordinary matter and have yet to be detected directly these days. So basically, in order to detect these WIMPs, there are huge laboratories set up across the world with these massive detector machines. And one of these laboratories is basically in Italy, and they have these cool detectors called dark side detectors. And they're these massive machines that have these argon time projection chambers, which sounds kind of fancy, but they're really important, and they capture WIMPs, like signals of WIMPs, and analyze them. And another candidate is known as axions, and they're extremely lightweight particles and sterile neutrinos, which are a type of neutrinos that don't interact via weak nuclear force. And these particles also offer potential explanations for dark matter's elusive nature, and still they all require more explanation and more experimentation to really figure out what dark matter is. So dark matter still remains super elusive despite all these decades of research and experiments in machines and laboratories and such. Its exact composition still can be identified, and despite it being everywhere, we don't even know what it is. And this really tells us why dark matter is like a thrilling quest, and it involves so many different scientific disciplines like astrophysics, particle physics, astronomy, and such. And scientists around the world are continuing to conduct these massive experiments and observations. They're really aiming towards detecting what these dark matter particles really are and uncovering new clues about its nature. And the quest for understanding still continues, and it has a really big impact on astrophysics today. So dark matter also tells us a lot about the universe, and its influence extends far beyond individual galaxies, and it basically shapes the evolution and structure of the entire universe. And you might be wondering how, and I'll tell you. So basically, its gravitational pull affects how matter is distributed on cosmic scales, and this leads to the large-scale formation of the galaxy clusters we talked about before. And astronomers are understanding how dark matter is driving cosmic evolution, and it provides a vital information in understanding the universe's past, present, and future. And it influences fates and predictions about what the universe really become in the future. So people might confuse dark matter with its basic brother, dark energy, and they're both similar but different. Because both are still named for their mysterious nature and lack of direct evidence, they still play distinct and different roles in the universe. So dark matter primarily affects the gravitational dynamics of galaxies and cosmic structures, but dark energy is thought to be responsible for the observed accelerating expansion of the entire universe. Because you guys should know that the universe is constantly expanding. But these guys are still different, but they still work together to constitute vast of the universe's total energy content, and they really work together to highlight the important and mysterious universe. Now that we've talked so much about dark matter, we hope some of you guys might be interested in it. And the study of dark matter has tons of educational and career opportunities for aspiring scientists. And students like you guys should be interested in physics, astronomy, astrophysics, and cosmology, and should even pursue undergraduate and degrees in these fields so they can research in the future. And maybe one day, even you could be someone who helps to figure out what dark matter really is. And basically, that's it. That's all we have today in today's episode of the STEM Spotlight. We hope you enjoyed, and I'm your host Vignesh, signing off.